Section 3.2 3D Modeling to create 3D print-friendly architectural designs. Now, let's discuss how to create 3D-friendly architectural designs. To help demonstrate the concepts and design techniques in this section, I will be using a 3D modeling CAD software called SketchUp. SketchUp is a free software developed by Google that's easy to use, and it's a great tool if you want to create 3D architectural designs quickly and efficiently. No, we're not getting paid to promote SketchUp, and if you're already familiar with another 3D modeling CAD software like AutoCAD, Revit, Maya, Virtual Architects, 3ds Max, Rhino, ArchiCAD, or virtually any other architectural CAD software, then of course you can feel free to use the software you are most comfortable with. They can all perform the same or similar functions to what we will be demonstrating in this section using SketchUp. If you're interested in downloading SketchUp for free, then you can go to sketchup.com/plansandpricing/SketchUp-free. The first design consideration we'll cover has little to do with the design of the walls themselves and everything to do with the capabilities and constraints of the printer. You may remember from C3D1100 that the most current OptiScore printer model has a maximum print radius of 5 meters, which is approximately 16 feet 5 inches. The proper abbreviation for maximum print radius is Rmax. Moving over to our 3D model, we can start out by using the line tool to create a cross, which will be used to represent the location of the center of our printer. Then, we can use the circle tool to draw our Rmax, starting from the center of the cross and extending outwards to create a circle with a 5-meter radius. I'll also add in an additional annotation to show that this is the Rmax, which equals 16 feet 5 inches, or 5 meters. The next constraint is the minimum print radius, or Rmin, which is equal to 1.2 meters, or 4 feet. Once again, I will use the circle tool to create our Rmin by selecting the center of the cross and then typing in 4 apostrophe, or 4 feet, followed by the Enter key. Again, I will add in this annotation to show that this smaller circle represents the Rmin, which equals 4 feet 0 inches, or 1.2 meters. Next, I'll use the brush tool to color the printable area green and the non-printable area inside of the minimum print radius the color red. If we right-click on the green printable area and select Entity Info, we can see that the total print area from any one position is 795.15 square feet, which is approximately 73.8 square meters. We are going to be using this drawing a few more times, so I will select everything that we just drew and create a component titled Printer Constraints. This groups the drawing together and makes it easier for us to copy, paste, and move the printer constraint drawing around our floor plan later on. When it comes to laying out an efficient, print-friendly floor plan, the Rmin and Rmax are certainly important numbers to consider. However, the beauty of this 3D printer is that you have the freedom to print massive buildings in multiple sections. Gantry printers may be large, but they're quite limited when it comes to max print area because they are not physically capable in most cases of printing large continuous buildings in multiple sections. Nonetheless, when designing a floor plan for an OptiScore printer, it's still important to consider the Rmin and Rmax for the purpose of efficiency. Let's imagine that you're designing a floor plan, and we'll use a model home that we actually printed as an example. You know that the maximum print radius is 16 feet 5 inches, which means the maximum print diameter is 32 feet 10 inches. With this in mind, you draw a rectangular house with exterior walls measuring 32 feet by 28 feet, and you choose these lengths because they are both less than the maximum diameter of 32 feet 10 inches. Do you think that this home can be printed using a single print radius? Although the dimensions of the home are less than the print diameter, look what happens when we take our print area drawing and set it on top of our house that measures 32 feet by 28 feet. You can see that the corners of the structure fall outside of the maximum print radius in this area here in red. You can also see that the wall at the front of the house leading out to the patio also falls inside the minimum print radius. The solution is simple. Just print the home in two different sections. Here, you can see that using two different print positions provides more than enough combined print area to print the entire structure. You know, it only takes about 30 to 45 minutes to reposition the printer, recalibrate, and begin printing the next section. So the decision to use two print sections should be an easy one to make. Now, let's say you want to add a 3D printed wall to create a bathroom inside of this home. And although there are a few places to put it, let's say the client wants to put this bathroom at the front of the house, in a place where this new bathroom wall will conflict with our second print radius and cut right across the minimum print area. This leaves us with two options. We can either relocate the two print positions in a way that all of the walls are included within the printable area, or add a third print position. Your first option should always be to attempt to relocate the two print positions, because, if possible, it's technically the more efficient option. However, with the addition of this new wall, there's nowhere that we can relocate the printer and still capture all of the walls within the printable area. This leaves us with option 2, which is to add a third print position. Again, adding an additional print position is simple, and the total transition time for 3 print positions is only about an hour or so in total. 1 hour of extra construction time is a small price to pay, especially when you compare it to the 7.7 months it takes to construct the average American home, or the maybe 100 or more years that this 3D printed home will likely be around for. Here, we can see that adding a third print position enables the entire building to fit comfortably inside of the combined print area. It also gives us a lot more flexibility when it comes to repositioning the printer, which can help reduce transition time and overall print time. This is because the printer does not need to be physically positioned in the precise location on the slab in order to print the walls in the correct location. In fact, the printer operators can technically position the printer in any location, as long as the wall section's toolpath is within the printable area, and the printer can move freely without hitting any obstacles or obstructions. As we'll learn about more in a later section, this is because part of the calibration procedure involves snapping the G-code to the slab, which is the process of digitally repositioning the toolpath in relation to the printer's current position. In essence, we adjust the position of the digital 3D model because this is faster and easier than trying to physically move the printer into the exact perfect location. The main point here is that the number of print positions should not be your number one priority during the initial layout of your floor plan. I've seen architects start the design process by focusing all of their attention on minimizing the number of print positions and maximizing the printable area, when in reality, they should have started by creating a functional space designed to serve the people who will live, work, and play in their creation, not the machine that makes it. If your first step in creating a floor plan is to design around the printable area, then you could really be limiting yourself, and you're more likely to overlook better design options that would have nurtured happier, healthier occupants. Efficiently planning out your print positions is important, but unless you're planning a tiny home that needs to fit within a single print position, it's typically best to wait until you've already established a basic floor plan that achieves your building's purpose and design goals. Once these goals have been achieved and you're happy with the basic floor plan, then you can move on to review the constructability of the design, plan print positions, and make adjustments as needed. With that being said, there are some tips to consider during the earlier phases of your print-friendly architectural design process. The first design tip is to consider the type of walls you will be using throughout your building. You should remember from the previous section that there are different types of 3D printed wall systems, each of which have their own unique benefits and applications. For example, if you already have decided that you're going to use 12-inch printed block walls on the exterior to take advantage of that higher R value, maybe 8 PB walls on the interior for their durability, and possibly a few hollow printed walls on the interior, then it's a good idea to make sure that your floor plan accounts for these wall thicknesses. To better understand this process of accounting for wall thickness, it helps to demonstrate the process of transforming a floor plan that was originally intended for, let's say, a stick-built home into a new floor plan for a 3D printed home. Let's imagine that you recently found a design for a stick-built home and you really like this floor plan. Here's one that we can use as an example. Now, I know that everyone has their own unique tastes and preferences, and this may not be it. But for demonstration purposes, let's pretend that this 2,000 square foot American dream home is everything you ever wanted. With one exception, it's a wood-framed home. We know that wood is flammable. It's susceptible to rotting, mold, termites, and pests, and maybe we aren't too happy about the fact that harvesting all of the trees means that animals will need to lose their homes just so we can build ours. Whatever the reason, you choose to 3D print instead. And your first step in converting these stick-built home designs into 3D printed home designs is to correct the wall thickness. We can start by importing an image of this floor plan into SketchUp. Then, we can use the line tool to trace the exterior walls of the building. Next, we'll offset the line 12 inches inward to reflect the 12-inch thick exterior walls we chose to use. It appears the exterior walls on the original plan were already about 12 inches thick, so let's add in our windows and doors, and then turn our attention to the interior walls. These interior walls are 4.5 inches thick, and we know this because interior wood-framed walls are constructed using 2x4 studs and gypsum drywall. Contrary to what the name suggests, the true dimensions of 2x4 wood studs are actually 1.5 inches by 3.5 inches. Assuming half-inch thick gypsum drywall is used on both sides of the wood studs, we're left with 4.5 inches of total wall thickness. However, we are 3D printing this house, so we want to start by converting these interior 4.5-inch walls into either 8-inch printed block walls or 6-inch hollow printed walls. One thing to keep in mind is that many municipalities require hallways and doorways to be a particular width to ensure buildings are accessible and easy to evacuate in the event of a fire. This is why it's typically best to leave the dimensions of the hallways unchanged to maintain a wide enough corridor for ingress and egress, especially if the plans you're starting with are already code compliant. The hallways in this floor plan all measure 3 feet wide, so we'll move the face of the walls opposite to the hallway an additional 3.5 inches outward. This way, the overall wall thickness will increase from 4.5 inches to 8 inches, but the dimensions of the hallways will remain the same. Next, we'll do the same thing to the remaining 4.5-inch interior walls until all of the walls are the desired thickness. You may notice that the process of offsetting the interior walls to account for the proper 8-inch 3D printed wall thickness will slightly reduce the size of each room. Although this difference is quite small, you can always offset the exterior walls outward to gain back that extra square footage. But to keep things simple, let's leave the original exterior dimensions of the home unchanged. This way, the home's footprint will remain the same, and we can likely avoid modifying the foundation and roof plan. Now that our walls are the correct thickness, it's time to address the rough opening dimensions for the doorways. First, it helps to understand the difference between a door's nominal dimensions, its actual dimensions, and its rough opening dimensions, because they're very different things. Let's say the product specifications for our front door say that the nominal dimensions are 3 feet in width by 6 feet 8 inches in height. These nominal dimensions refer to the size of the door itself, not including the frame. If you're installing a pre-hung door, then you may also find a set of actual dimensions that do include the size of the door frame, which in this case is 3 feet 2 inches in width by 6 feet 9 inches in height. However, the rough opening dimensions refer to the size of the hole in the wall where the door will be installed, which is typically even larger than the door's actual dimensions. This creates a small gap between the door frame and the wall where shims are installed to level and plumb the door inside of the rough opening. This means our rough opening is 3 feet 3 inches in width by 6 feet 9.5 inches in height. When designing a 3D printed home's floor plan, it can help to use the rough opening dimensions for the windows and doors instead of the actual or nominal dimensions, because the 3D printer will be creating the rough opening. If your door is designed to be installed into a CMU block wall, then the rough opening width in the product specifications is most likely the same rough opening width you will use for the 3D printed home's floor plan. However, some pre-hung doors are specifically designed to be installed inside of a wood-framed wall and not a CMU wall, which means they are designed to be attached to wood studs. If you are using these types of doors, then you will also need to install wood bucks inside of the rough openings, which will be attached to the 3D printed walls and serve as the anchor points for these pre-hung doors. Assuming we will use 2x4 wood studs to frame out the wood bucks, we will need to account for the additional thickness in our rough opening calculation. This will increase our rough opening width from 3 feet 3 inches to 3 feet 6 inches, and our rough opening height from 6 feet 9.5 inches to 6 feet 11 inches. Going back to our floor plan, we can see that the door leading into the house from the garage is 3 feet wide, but we want to modify this dimension to reflect the door's rough opening width. Assuming that we will use a pre-hung door, which does require wood door bucks to be installed, we will need to increase the doorway's rough opening width from 3 feet to 3 feet 6 inches. Typically, I would offset both sides of the rough opening an equal amount to keep the center of the doorway in the same location. But in this particular case, you may notice that I'm only offsetting the left side of this doorway when making this rough opening adjustment. This is because we can see a dryer on the right side of the doorway, and we want to leave plenty of space for the door to swing open freely without hitting the dryer. Then, I'll simply repeat the process of adjusting the rough opening width for all of the doors in the house, paying close attention to avoid any potential conflicts that would obstruct the door from opening and closing freely. It's also important to remember that there will likely be different types of doors used throughout the house, so always refer to your window and door schedule to ensure you're using the correct dimensions. The same principle for rough opening dimensions also applies to windows, so we will repeat the same process for all the windows throughout the home. At this point, we have modified the original plans to account for the thickness of 3D printed walls and adjusted the rough opening dimensions to accommodate the windows and doors. Now, we can start considering the different print positions. This is where our printer constraints drawing template that we created earlier can come in handy. There are 4 things to consider when laying out print positions. First, you want to fit all of the printed walls within the combined print area from all of the print positions. Second, you want to consider the order or sequence in which the wall sections will be printed. Third, you may want to consider which walls, if any, may be more efficient to wood frame rather than 3D print. And four, to consider the location of control joints or abutments in the building where two different print sections join together. The goal is to print the entire building in the most efficient way possible, which typically means minimizing the total number of print positions. This process can take some trial and error, and the larger the building, the more possible print configurations there could be. It can help to start by focusing on the exterior walls first. I like to place my first print position at one corner of the structure and then move sequentially along the perimeter of the building until all of the exterior walls are captured. I will copy the floor plan and paste a duplicate floor plan right next to the original, which we'll use to plan the print positions. This way, I always have the original plan to refer back to in case we end up making modifications to the duplicate. Next, I will try placing 4 print positions near the exterior corners of the building to see if we'll need additional print positions. It looks like there are still some portions of the exterior walls near the middle of the home that did not fit into the green print area of these first 4 positions. So let's go ahead and add 2 more print positions here and here, and a third additional print position in bedroom 3, so that all the walls are captured within the combined printable area. Now, you can see that a few of the walls fall within the red minimum print area, which at first glance may seem like these walls cannot be 3D printed unless additional print positions are used. Thankfully, this problem can be easily solved without moving any walls and without increasing the number of print positions. This is because we are printing this building in multiple sections, which means that these small portions of the wall which conflict with the minimum print radius can be printed at the next position, so long as they also fall within the printable area of this next position. For example, we can see here that a small portion of the wall in the study room cuts through the red minimum print radius at this position. However, we can adjust the location of this other print position near the center of the home so that that same portion of wall can be captured within the next position's green printable area. In practice, we would print this position from the study room where the conflict occurs first, before printing from the next position where the conflicting portion of the wall will be filled in. Now, before we officially break this building up and to define which walls will be printed at which position, let's assess the possibility of replacing some interior 3D printed walls with wood-framed walls instead. This is most commonly done in areas that homeowners tend to renovate later on in the building's life, such as kitchens or bathrooms, which also tend to have a significant amount of plumbing and electrical work inside of the walls. In this particular floor plan, neither the kitchen sink nor the dishwasher are attached to a wall, but Bathroom 2 has 3 separate fixtures that require through-wall plumbing in an interior wall. Moreover, if we choose to wood frame the walls in bathroom 2, then we can move this print position to the center of the bathroom and eliminate this print position altogether. This is a great example of value engineering, which we will cover in section 4.1, because this minor change will speed up construction time, reduce the number of print positions, and make the home easier to renovate later on in the future. Finally, we can break the building up into multiple sections, define which walls will be printed at each position, and determine the order in which the sections will be printed. Again, this process can take some trial and error, but let's try to start with this section at the back corner of the home as our first position, seen in red. We will leave one portion of the wall open so the printer can easily drive to the second position near the front of the home, seen in orange. Although this portion of the wall could have been printed from the first position, we will purposefully wait to print this portion from the second position to avoid trapping the printer inside of the first room. After printing section 2, we will move to print position number 3, seen here in yellow. Here we will print the extra walls which were inside of the minimum print radius at position 2 in the study room. Then, we will move to print position number 4, seen in green. Similar to section 1, we will wait to print a portion of the wall between the kitchen and hallway, which will allow us to easily drive the printer to the next position. Once these walls are complete, we can drive the printer to the 5th position, seen here in blue. Here we will print the remaining walls in the kitchen and hallway and leave an opening so we can easily drive the printer into the final position. Here at print position 6, seen in purple, we will print the garage and then exit through the garage door opening. Once printing is complete, the 2 additional wood frame walls for bathroom number 2 can be installed. Before we conclude this section, I want to point out that this process of converting standard floor plans into print-friendly floor plans may seem challenging for those who are not familiar with 3D CAD software or architectural design. You may even be a licensed architect who wants a second opinion to make sure that your floor plans are fully optimized for printing before going out into the field. That's why APISCore offers an affordable constructability review service where our team of experts can analyze your architectural designs and convert them into fully optimized print plans to help you succeed. Whether you need everything from floor plans to G-code or just a few simple recommendations, our team is standing by to support your efforts and help make your project a success. We are also developing a more advanced certification course specifically designed for architects, engineers, and G-code developers. These courses will provide the tools you need to fully master the entire process of construction 3D printing.